The software has been worked on for the last 6 years, and the idea that we have, the vision we're working towards, is to enable new research, because the architecture is very different from anything out there. And we are seeing some examples shown on this slide of use cases in the industry and in research across a spectrum of use cases, from drug discovery to finance to high energy physics to weather forecasting. So it would be very, very exciting to see researchers who joined this call develop new things with this different architecture. So Chad has shown this slide in a different perspective with the 2 wafers in it. But the software portion, I wanted to kind of show it once again, introducing the terms that I will be using here. On this floor plan, you will see cores that are marked with these red squares, and then each core has memory, which is local and private to that core. And the cores can talk to each other through the IPU exchange fabric. And again, the numbers are here, 65 terabytes per second between the cores and the memory, 11 terabytes all-to-all connectivity between the cores, between the tiles, and IPU links and PCIe links to the host. So every operation, as you program the chip in TensorFlow or PyTorch or Poplar, which is the name for a framework, the compiler, say if you take a matmul in TensorFlow, the compiler will try to leverage all the available parallelism, all the available cores and threads on the cores to reduce the number of cycles an operation takes. So a matmul will be distributed across the available tiles, and then every tile will produce some partial results that will be reduced, moving the data between the cores, and then it can be done in a couple of steps like that. The compiler takes care of data movements between the cores, and as a programmer at the very low level in Poplar and C++, you have the control over what codelets and what tensor slices go to which tiles. And then if a specific tile will require a set of data, a slice of a tensor from a different tile, it will be moved to that destination tile during the exchange phase in the BSP. So BSP, as Chad mentioned, is the core paradigm that is important to understand the software. And it also makes it easy to program this almost 9,000 threads running in parallel, 14,072 parallel CPUs. Would not be easy without this set of fundamental building blocks in the architecture. So BSP maps very naturally onto the computational graphs, or I should say vice versa. If you have a computational graph with some input data or tensor slices that are consumed by compute vertices that in their turn produce some output tensor slices, you can represent it as a series of exchange and compute phases in the bulk synchronous parallel execution with synchronization after the computation. And this ensures that before a tile starts a computation, it has all the data that it requires for the compute vertices scheduled to it. And then this synchronization ensures that at a given point in time, at a given cycle, the chip is in a deterministic state. We know what has happened, and we know what needs to happen to enable the next compute phase. And we will be able to move the data around to make sure all the data is moved locally to the destination tiles. During every compute phase, all the cores operate on their local data. There is no cache or memory hierarchy on the die, on the chip. So you will have 900 megabytes distributed across 1472 cores, and every core has about 638 kilobytes of data. So this is an important piece of information. Any questions so far, please?
There was one in the chat that was asking if in-processor memory is entirely managed by the software compiler, or does it also get controlled by hardware? I wrote an answer in there if you have anything to add to that. I basically said that each core has dedicated memory, and so while it's computing, it fully controls it, but the exchange part and where it goes is managed by the compiler.
Yeah. So yeah, there is nothing controlled by hardware like cache. We do not have a cache, and we can say that the memory is fully controlled by the compiler, because during the execution, you will have tensor slices allocated to a core, to any given core, as inputs and outputs to take information from, to write information to. It will be put in the memory by the compiler. And similarly, for the data exchanges, the compiler will take care of, well, getting the information from the right set of addresses in memory and moving it, putting it in the destination set of addresses on the destination tile. Thanks for the question. So yes, there is parallelism inside the chip that is enabled by BSP, and there is parallelism between the chips, again, as chat showed, with this kind of topology within a chassis, and then a torus between the chassis, as shown on this slide. Let me get a question. What information is stored in SDRAM? Okay, so an M2000 machine, or BowPod64, as we call the newer generation, which Argon has SDRAM of 128 gigabytes in size. Since it is slower versus the normal CPU memory, I think the slide listed 20 gigabytes per second, that can be used to offload data that is used infrequently. For example, the optimizer state. Imagine you are training a large model and you need to process multiple batches, which takes some time to do, and you do not need the optimizer state as you are computing the loss, for example, and then you accumulate the gradients. Then you can load the optimizer state every n batches, maybe every 100 or 1,000 batches, and then update the weights accordingly and update the optimizer state, offload it to the external DRAM or streaming memory, as it's called on these slides. It's not 512 gigabytes per machine, it's 128.
Yeah, it can go up to 256 for BowPod2000, but 128 is our default config.
Yeah. But theoretically, it can be used for anything, of course. It's just a scenario that is typical, storing the optimizer state that I described. We actually use that external memory to enable large language model training. For example, the GPT-3 training example that we have in our examples public repository that leverages the external memory for waits and activations to store those. And that repository, I will touch on that tomorrow, has a nice README file that details the set of additional things we do to leverage the parallelism and increase the overall bandwidth to that memory. Let me know if it answers the question. And thanks for that. In terms of developer ecosystem, we have a policy toward the idea of being very, very open in what we do. And this includes the developer page on our website, which does not require any logins or accounts. And with that, you can get access to all the documentation there, examples and tutorials that are in public GitHub repositories, and Model Garden as a tool to quickly find the model that is of interest to you among the examples of optimized models that we have, and all kinds of other resources to make it easier for you to start using the IPUs or answer any of your questions. Since there is no login required, you can just Google Graphcore and your question, or Graphcore and a name of a method you're interested to get more information on, and typically you will land on the right documentation piece, which is a very nice user experience, I think. Having our code in open, in public repositories.
One other quick comment on the last one, though. Sorry if you already said this already, but we also have a community Slack channel as well. So if you're not able to find what you need in the documentation and tutorials, you can always ask the Slack channel, and we have people from Graphcore monitoring that.
Yep. Thank you, Chad. I will have a link to that Slack channel, a link to join that one at the end of the presentation, every presentation actually. But that's a great point. So we have open sourced many of our tools in the SDK, including popular libraries. Again, we call our software SDK Poplar, and popular libraries or poplibs among the public repositories in the Graphcore organization on the GitHub. And you can use that to get inspiration when building maybe some custom ops in TensorFlow or PyTorch, so that you do not start from scratch. Basically, you can reuse the netmol implementation or any element-wise implementation that's out there. And this, I think, makes us different from other vendors that did not open source their libraries. And also our implementations of IPU-specific TensorFlow and PyTorch wrappers are also there. And of course, the examples. We have a bunch of 15 or so minute videos that helps you get from zero to a decent understanding of a topic like PyTorch or TensorFlow or Poplar, and a lot of resources. In addition to that, white papers and webinar recordings, research papers. So can be interesting to dive into that. In terms of framework support, probably I will mention on this slide that we support high-level frameworks, TensorFlow, PyTorch, PyTorch Lightning, PyTorch Geometric, Hugging Face, which is typically PyTorch-based. And then in TensorFlow, it will be Keras, and other frameworks, Paddle, Halo, that go through Onyx and PopArt for us. So I will show in this presentation and after the short break that it is easy to port an application from CPU or GPU based TensorFlow or PyTorch code to the IPU. Other components of the software stack are shown on this slide. And you again have the frameworks at the top, and Jupyter Notebooks is a nice way to interact with the IPUs. Under the high-level frameworks, you will see 4 popular SDK pieces like TensorFlow compilation uses XLA to produce the intermediate representation of the graph, and then it gets lowered to popular library operations during the compilation of the graph. PyTorch, for example, currently is traced, meaning that the forward pass of your model will be traced using the dispatcher interface, and the extracted set of operations goes through PopArt, which stands for Popular Advanced Runtime. And then it's mapped to a set of popular library calls, and then a lower level graph is produced. And then the lower level parts of the stack include drivers and the compiler, of course. We have a bunch of examples of machine learning applications across different domains, and that model garden is a nice interface to discover those. And I've mentioned the components of the developer ecosystem. Pop Vision tools will be covered in the session tomorrow. That basically the idea is to help you get as much visibility as possible into what's happening on the IPU and on the CPU as your graph is executed. And then at the system level, we integrate with other monitoring tools and orchestration frameworks like Slurm, for example, which is used on the BowPod64 at Argonne ALCF. The model garden page looks like this, and you have a nice filter on the left that allows you to filter by the machine learning domain, for example, GNNs or speech processing, or you can just search by the model name here. And then typically a model will have a link to try it in Paperspace, which is one of our cloud partners, on a Colab like service, so notebooks attached to IPU machines, and then a link to the repository in GitHub that has the code for this specific model. And the coverage in the model garden is pretty broad, as shown on this slide here. And it's, of course, growing rapidly. Pop Vision, I've also mentioned, this is a quickly growing tool and very mature as well. The graph analyzer helps you get visibility in on the IPU side. So what happens at a given cycle on a given core, for example. And then the system analyzer helps you see what's happening in the threads on the CPU side. Maybe the data pre-processing, data preparation on the CPU takes too long, and you will want to maybe try and dive deeper and understand what is happening. Maybe it's your network attached storage that is slower than expected, maybe something with the way your script opens files. And this is an example of a trace by the popular PopVision graph analyzer with the cycles on the x-axis, the horizontal one, so the time goes from left to right. And this is the flame chart of the operations that are executed at a given cycle. And this is the BSP trace with the tiles from 0 to 1471 going in the vertical direction. So a lot of transparency there. Any questions so far? And please feel free to interrupt me at any point. I'm very happy to keep it interactive. Okay. So I will cover 3 frameworks today in the slides. Keras and PyTorch at a high level, and then Poplar, C++ based at a deeper level. And then Keras and PyTorch, which are, I understand, the normal ways for the researchers to interact with accelerators. These will be covered today after a short break in more detail. So Keras on IPU is based on a public repository that we maintain and that you can take a look at. We have implemented a couple of IPU optimized model classes for the functional model implementation and the sequential model. So a set of layers that follow each other. And we have added a few optimizations that make it faster and easier to run the program on the IPU in Keras. You will find also a few operations that are optimized for the IPUs. An example would be LSTM layer or optimized dropout layer that, for example, uses in-place operands instead of creating a separate copy for that. The 2 optimizations mentioned on this slide, I think, are very typical when running a program.
Hi, excuse me.
Yes.
I'm wondering if you're thinking you're showing a different slide than you are. We're seeing the open source slide.
Oh, the open source. Oh my God. That's bad. Sorry about that.
Alex, I can see the Keras on IPU.
Keras on IPU is what's supposed to be on the screen.
Huh.
Maybe somehow mine is stuck.
Sorry about that. Let me stop sharing and then share again. So who can see Keras on IPU, please?
It's showing. Yeah. Keras on IP.
Okay, clearly something on my end, although I'm just now seeing a blank screen, so I'll figure it out, I suppose.
Yeah,
no, that's okay. Go on. I'm thinking it's on my end, so.
Okay, there will be the recording. The slides are public. So one of the things you could do is download the PDF from that page, and you will see the same thing as I'm projecting.
Perfect. Thank you.
Thank you. Sorry about that. So the first optimization, I will briefly touch on it now and then discuss in a bit more detail after the break today. On-device training loop. That simply means that as you execute your program on the IPU, it is typically initiated from the CPU, then the program will do some work on the accelerator and then stop and return control to the CPU, so to speak. So there is an overhead in launching the program, streaming the data to the accelerator, getting the results back. In order to amortize this overhead, it is recommended that you run a loop on the accelerator on the device and process more than one batch. For example, you can run inference and process 10 batches or 100 batches at a time, and you will see the predictions stream back to you as they are produced. So the engine will run, you will be getting the results in real time, but the overhead of starting and stopping the engine will be avoided. And similarly for training, you can run training, you can do multiple gradient steps with a single engine run. And it will be much faster versus making a single step at a time. This is what we call on-device loop. And then gradient accumulation is a variant of that, where instead of making a gradient step during model training every time we launch the engine and produce the gradients, we process several batches and accumulate gradients from those before applying the gradients to the weights, making that gradient step. So these are the two typical things that help optimize for performance. And this slide shows a comparison between the GPU program on the left and IPU program on the right. Is dynamic loop bound supported? A question in the chat. It is. It is definitely supported in Poplar